I sung and tap dance long enough. We'll at least get a quorum. Sing and tap dance? Did I say song and tap dance? Anyway. Are there any questions?
Number 44.
You said 24?
Yeah, 24 too. Yeah. 24.
Okay, the half-centimeter diameter plastic sphere used in a static electricity demonstration as uniform charge distribution of 40 picocoulombs charged on its surface. What is the potential near its surface? So 0.5 centimeter. And then the uniform surface charge density of 40 picocoulombs. All right, we talked about that. If I have a spherically symmetric distribution of charge, if I'm inside, my electric field is 0. Well, it turns out that the electric field is the magnitude of the electric field is the change in the potential with respect to distance. Oh, wrong class. Technically, is negative delta V. Which means since the electric field is 0 inside, the electric potential is constant. So if that's 0, then this is 0. In other words, the change in the potential is 0, so it doesn't change, so it's constant. So the electric field here is the same, right? Basically at the surface is the same as inside. So when they say near the surface, it doesn't matter which side of the surface we're on. So if I'm just outside, then I can, and with spherical symmetry, I can assume it's a point charge, centered here. And so if the potential is equal to 0 at R is equal to infinity, which is a general assumption, although it's not stated, so you could legitimately get away with, since this was not stated, the potential was 0 because I said so. However, probably not the intent. So the potential, just plug and chug into the point charge formula, kq over r. So that'd be 9 times 10 to the 9th times 40 times 10 to the negative 12th, which is pico, over 0.005 meters. You get 7 point something.
On yours, it says you got like, for the bottom part, you got 2.5 times 10 to the negative 3, and then would equal 144.
Yep. All right. Is this the right book? Nope, that is not. Right, I'm gonna have to see what the solution says.
This one, okay.
24.
Is it this one or the top?
It's,
Yeah.
did they say that the diameter was a half centimeter or?
It says, yeah, the diameter is at
Ah, okay. My mistake.
0.5.
That's 0.5 centimeters. Therefore,
Okay.
the radius is 0.25 centimeters.
Okay.
Does that answer your question? Anyone else question on this? Chapter 19, problem 24. Any other questions?
For
Liz?
problem 3, maybe it's just my oversight, but I couldn't figure out how to do part C.
So problem 3,
Part C, what voltage would be needed to obtain this energy?
need to attain this energy. A bare helium nucleus, 2 positive charges, yada yada mass. And they give you a speed. So the first part is plug and chug it to the formula that all of us know and love. Then convert it to electron volts. What voltage would it need to obtain this energy? Definitely have my interpretation of this. Just give me a moment. Alright, so B is just alright, so I'm interpreting it as if you started at rest, what voltage would be needed in order to get it to 2% of the speed of light. That's my interpretation. So, if it starts at rest, K is 0. Then I know that the change in the electric potential, in other words, the voltage, is equal to the change in potential energy divided by a test charge. I know that the change, since we're dealing with electric forces here, which are conservative, energy is conserved. So the change in potential energy plus the change in kinetic energy should be 0. So the change in kinetic energy is the negative change in potential energy. So that you already found. That's going to be equal to negative chest charge times, or charge times the change in potential, the electric potential, or voltage. We know what Q is. So delta V would be delta K over negative Q. That you found in part A. Negative Q would be the change in, negative Q would be the charge of 2 protons, which would be negative 2 times 1.6 times 10 to the negative 19 coulombs. And so you'll end up with a negative potential, which makes sense because we're losing potential energy in order to gain kinetic. Does that fit with the way that, did I interpret that correctly? You're not sure?
No, I don't know. I trust you though.
Did you have a question about?
No, I just didn't do it, and I wanted to know how to do it.
Okay. Other questions?
63, both A and B.
63, what is the energy stored in a capacitor of a heart defibrillator charged at a certain voltage? Find the amount of stored charge. So that should just be a matter of looking at Chuck. So at the bottom of page, well, 760 in the version I have got, in the summary section, they give you the energy capacitance, or the energy of a capacitor, sorry. QV. I know this is for a capacitor. I know that for a capacitor, capacitance is equal to technically delta V. Absolute values of everything. So then it's just a combination of, I can solve for Q, plug into here, and I have it in terms of C and delta V. I can solve for delta V in terms of Q and C. So there are three variations of the formula. Mm-hmm. So in this particular problem, they give you the capacitance, so they give you C, and they give you the voltage. So I want this in terms of C and V, or delta V. So Q is equal to C delta V. Plug that into here, and I get 1/2 C delta V squared. And now it's plug and chug.
Okay.
That's A. Part B, find the amount of stored charge. Well, they give me C and delta V. The stored charge would just be C times delta V.
My main concern was A, but I wanted to make sure that B didn't correlate to A and then this other one.
You could if you wanted to, but you're...
Yeah, they could just do that. That's perfect.
Other questions?
I'm
Please.
gonna use my phone as a calculator. I left mine at home.
Yeah. I can get you one also.
Oh, yes, that would be better.
Okay,
I
Thank you.
need one too.
okay. When I go grab the quizzes, I'll grab the calculators.
Yes.
Other questions? All right, Luis is done. Erica, you look like you want to ask something, but,
No, I don't think I do.
okay, but no, good. Abby? You good? All right. Then, I'm going to pause this, go grab quizzes, and then hopefully, 5 more people show up.